This is explainer video for long homework 1, question number 3. Question 3a starts by asking to argue whether or not the vector u with components 2, 3, and 1 is part of the same subspace spanned by v with components 3, negative 1, and 2, and w with components 1, 3, and 0. And so if we want to have a visual representation of this, we can draw a graph where vector v maybe goes like this, and vector w goes like this. And so these two vectors will create this plane can be considered the subspace. And so our question is, does this vector u fall within this subspace? And so the way we can figure this out is we can see if that we can have any linear combination of the components of u and v and w in order to get to u, and we can write it out like this. We can say that number a times 3, negative 1, 2 plus b times 1, 3, and 0 will ever equal 2, 3, 1, like this. And a and b can be any number. And so we can create a system of equations with 3 equations and 2 unknowns. So we can say 3a plus b equals 2, negative a plus 3b equals 3, and then 2a plus 0 is going to equal 1. And so we can start off with the easiest one, which is this first equation right here. And we can say, well, if 2a equals 1, then a must equal 1/2. And so knowing this, we can plug this into this equation right here. And so we can say 3a, so that's going to be 3 over 2, plus b equals 4 over 2. And so we'll get that b also equals 1/2. Knowing this, we have to see if these two values will satisfy the third equation, which is negative a plus 3b equals 3. And so let's try that. Negative 1/2 plus 3 over 2 equals 3, which equals 2 over 2. However, 3 does not equal 2 over 2, because 2 over 2 will give us 1. And so we're going to say that since this final condition is not met, that the entire system of equations cannot be solved. That there's no solution. There's no a and b that will give us a some linear combination of v and w that will end up giving us vector u. So we're actually going to say that u does not lie within the subspace. So if u won't lie in here, it maybe goes like this. We don't know. And so because of that, they don't lie in the same subspace, and therefore the answer to this is going to be no. The vector u does not lie in the subspace spanned by vector v and vector w. Question 3b asks us to see if the unit vectors for v and w lie in the same two-dimensional vector space as the original vectors v and w. And so we're going to use a similar idea to what we did in the last question, where we're going to draw a picture and say that v and w make some vector space. And we're going to see if these two unit vectors will still fall within this plane. And so what we can do is we can do again, what we did in the last problem, where we see if a linear combination of v and w can get us to these unit vectors. So let's say there's some a times v plus b times w, which will give us the unit vector v hat. And so since it's a unit vector, this value right here, this magnitude, is just a scalar number, which means that we can actually set one of these equal to 0, and the this a value just equal to this magnitude right here. So we can say that in the case for v hat, we can say that a is just going to equal 1 over the magnitude of v. And in this case, that's going to equal 1 over root 14. And then we can set b equal to 0. Because then we're going to get that 1 over root 14 times the vector v, so 3, negative 1, 2. And this just equals v hat. So we've proven here that this unit vector does lie in the same subspace, because we can say there's 0 influence with w, and that there's going to be a length of 1 v hat, like this. And we're going to do the exact same thing for w, where we say that av plus bw equals the unit vector w hat, where in this case a is going to equal 0, and b just equals 1 over the magnitude of w, and that's going to end up being 1 over root 10. And then we're going to see that 1 over root 10 times the vector w, that's going to be 1, 3, 0, is just equal to the unit vector w hat. And so from 0 influence by v and this influence by w, we're going to say that this also lies within the same subspace. So we've just proven that there is some linear combination of a and b, or rather vectors v and w multiplied by a and b, that can give us each of these unit vectors, which proves that they're in the exact same two-dimensional subspace, v2, as the original vectors v and w. Question 3 gives us a new vector, vector y hat, and it's asking to confirm that the vector is part of the vector space v2, which means that we can use the same strategy as before to see if the linear combination of v and w can give us y hat. And so to do that, we can draw our diagram again. We can draw vector v and vector w. And we want to see if vector y hat falls within this subspace. And so the way we're going to do that is using that linear combination method. Now you'll notice that if we actually just add these components together without considering a or b, we'll actually just get whatever's inside this vector right here. So we're it's going to be 3 plus 1 is 4, negative 1 plus 3 is 2, and 2 plus 0 is 2, which means that the a and b must be equal, and they must also equal 1 over root 24. And so we have proven by showing that the two variables a and b can be given a value that will allow a linear combination of v and w to give us y hat. And so we can write this as 1 over root 24 v plus 1 over root 24 w gives us y hat. Now, the second part of the problem asks us to argue as to whether or not the two vectors v hat and y hat form an orthonormal basis for v2. Now, orthonormal means that two conditions have to be met. First of all, both v hat and y hat must equal 1, the magnitudes of them, and they must also be perpendicular. And so we can first check this initial condition right here, and we can see that the unit vectors always are going to have a magnitude of 1. And so because of that, we know that this is correct, because 4 squared plus 2 squared plus another 2 squared gives us 24. Which, of course, when you multiply by the 1 over root 24 right here, you're going to get 1. And then for v, we know that v hat is going to be equal to 1 over root 14, as found in the previous problem. And so the magnitudes of both these vectors are going to end up being 1. Now, for the second condition, we need to prove that these are perpendicular. They're perpendicular when the angle between them, cosine theta, equals 0, which means that theta must equal 90 degrees. And so we can see if this is true by multiplying each of the components together, and if they sum to 0, that means the angle between them will be pi over 2, and therefore they will be, we can say that these vectors are orthonormal. So let's see if that's true. And so we can write right here that 4 over root 24 times 3 over root 14 plus 2 over root 24 times negative 1 over root 14 plus 2 over root 24 times 2 over root 14. And you'll see here that these are going to have the same denominator. And so because we need to see that if these will add to 0, so 12 plus 4 minus 2 is going to give us 14. And so 14 is not equal to 0. Therefore, these two vectors cannot be orthonormal because one of the conditions is not met where they are perpendicular to one another. And so, yeah, the main answer is going to be no, they do not form an orthonormal basis.